Adam, I was wondering what everything's made of. And so first of all, isn't everything made of atoms?
Yeah, all the stuff around us is made of atoms. I mean, there's the 95% of the universe where we don't really understand what it's made of, dark matter and dark energy. But putting that aside,
It's only a small thing.
The 5% of the universe where we do seem to understand what it's made of, it's all made of atoms or stuff like atoms, ions, which are atoms with missing electrons or extra electrons or stuff.
Okay, so hang on, wait. Atoms contain electrons, so you can actually cut an atom up into something smaller.
Atoms are not fundamental. They're made of other things.
Okay, so what are they made of? You mentioned electrons.
Yes, so atoms are made of electrons, which go around a nucleus, and the nucleus is made of protons and neutrons.
Okay, so protons and neutrons fundamental.
No, protons and neutrons are not fundamental. They're made of quarks. Specifically, they're made of two different kinds of quarks, up quarks and down quarks. One of them is two ups and a down, and the other one is two downs and an up. And I never remember which is which, but the point is atoms are made of electrons and quarks.
Okay, so that's three fundamental particles then, two quarks and the electrons. Okay, so is that what everything's made of then? There's two quarks and the electron.
Almost everything in the universe is made of those things. There are other fundamental particles, though. There's trillions of neutrinos passing through us right now.
All right, so we've got the two quarks, the up and down quark, we've got electrons, and we've got neutrinos. Is that it?
No.
Right.
Not even close. It turns out that there's a lot more fundamental particles than that. There's actually two more groups of four particles like that, which is just like our group of four particles, except sort of heavier. They have more mass. So there's actually six quarks, not two. There's the up and down quark, and those sort of form a pair. And then there's another pair, the strange and charm quark.
Okay, fine. Why are they called strange and charmed?
These things have names, and the names have very little to do with any properties of these particles. They're just given these names so we can keep track of them, which should give you a hint as to how complicated this is going to get. There's three pairs of quarks. There's the up and down quark, there's the strange and charm quark, and then the third pair of quarks is, well, they were originally called the truth and beauty quarks, but now we call them the top and bottom quarks, and the reason for the name change is silly, and I think we should go back to the original name because that's way better.
Okay.
But then there's also, there's other stuff. Like I said, that group of four, there's two more groups like that. They're called generations for no reason. There's also a thing called a muon, which is like a heavier version of an electron. And other than that, it's the same as an electron. When it first showed up in a particle accelerator, there was a physicist who said, "Who ordered that?" So there's a muon, and there's also an associated neutrino. So it turns out these neutrinos are paired up with these things that are like electrons. So there's the electron and the electron neutrino, and then there's the muon and the muon neutrino. And then there's the tau, which is like an even heavier and even shorter-lived electron, and the tau neutrino.
Right. Okay. So you've got the 6 quarks, and you've got 6 of these other things. What are they?
Yeah, the other things are called leptons.
Right. Okay. So 6 quarks and 6 leptons.
Yes.
Right. Now we're done. Right.
No.
Right. Okay.
Those are the things that matter is made of. We still have to talk about the things that mediate the forces between matter.
Okay.
So there are 4 known fundamental forces. There's gravity, which we know from everyday stuff. There's electromagnetism, which we also know from everything in our lives. Magnets, electricity, light.
Sure.
Electromagnetism is also what holds atoms together, and the fact that the chair you're sitting in doesn't fall apart. That's mostly electromagnetism. And then there's 2 other forces that are very, very short-range forces. They only act over the distance of the width of an atomic nucleus, which is like a millionth of a billionth of a meter.
Okay.
So really, really short distances. But these 2 forces, again, these very creative names that we come up with, one of them is very strong and one of them is very weak. So, of course, we call them the nuclear strong force and the nuclear weak force.
Fine. Okay. Well, we're at least being logical now. All right. So we've got 4 forces.
That's right.
So there's got to be 4 little particles, 1 for each force.
Not quite. So the particles that make up stuff, we call those fermions. These particles that carry forces, we call them bosons. There is one boson for electromagnetism. So electromagnetism works the way that you think it would, and it has a boson that actually a lot of people have heard of, the photon.
Okay.
And it's just a little packet of electromagnetic energy. And so there's photons whizzing around the room with you right now. But these other two forces, the nuclear strong force and the nuclear weak force, they don't really have just one. The strong force is what holds quarks together into protons and neutrons, and it's what holds protons and neutrons together into atomic nuclei. So that we call these things gluons because they're like glue. So the strong force has this thing called color, and there's three colors: red, blue, and green. These colors in the nuclear strong force, there's three of them, and so of course there are 8 of these particles that carry the force.
Right. Okay.
There's red up quarks and blue up quarks and green up quarks, and the same for every other kind of quark. So there's not 6 quarks, there's 18.
Have we talked about the weak nuclear force yet?
No, we haven't talked about the weak nuclear force. The weak nuclear force is carried by three particles: the Z naught and the W plus and minus, and those three things carry the weak nuclear force.
Right.
The weak nuclear force basically is responsible for certain kinds of particle decay, and it's also the only thing that neutrinos feel, except for very, very weak gravity.
Okay.
So there's 3 bosons for the weak force, there's 8 for the strong force, and there's 1 for electromagnetism, so I think that's 12.
Yeah, that's 12. And then you've got your 18 quarks,
Yep.
and we've also got the 6 leptons.
Yes, that's right. The electrons and the neutrinos and the
Right.
things like
Okay.
them. Yeah.
Are we done now?
No, we're still not done. We're still not done because it turns out that every particle has an antiparticle.
Oh, so you mean antimatter, the thing that makes things explode when you put it with normal matter.
That's right. Yes. It turns out that every single particle has an antipartner. Now, some particles are their own antipartner, like photons are their own antipartner. Some particles we've sort of already talked about their antipartners. So, for example, the W plus is the antipartner of the W minus, and the gluons we've already taken care of. That's part of why there's 8 of them. It's complicated. All of the other particles have antipartners. So there's not 18 quarks. I lied again. There's 36 quarks.
Right.
And there aren't 6 leptons, there are 12 leptons. And so I'm sorry, Mike, do you know how many particles we have now?
I'm still with it. So we have the 36 plus the 12, so that gives 48, and then there was the other 12.
Yes, that's right. And there's still just the 12 of those. So yes, that sounds like 60.
Okay. Oh, great. So we got a nice round number. We're done now.
No, there's still one more. There's the Higgs boson.
Okay. Right, now that I have heard of.
Yes, yeah, I think everybody's heard of the Higgs. So, yeah, the Higgs boson was the last one to be discovered. It is its own antipartner, thankfully. So there's not 2, there's just the 1. It's basically responsible for all the other particles having mass.
All right. So why 61? That's just untidy.
Yes.
This cannot be right.
I hope you can hear exactly how impatient and exasperated I am with this situation. It is completely insane. 61 just seems completely arbitrary. We have a good theory that explains how these 61 particles behave. It's called the standard model of particle physics. But the standard model is still pretty messy. I mean, it has 61 particles. It has something like 20-something numbers that you have to plug in that you just have to get from experiment.
And if I've been keeping track of this, we still haven't fitted gravity in.
That's right. We do have a very good explanation of it called Einstein's theory of general relativity, but no one's been able to find a way to unify general relativity with the standard model. And there are other things missing as well. We're missing dark matter and dark energy. We know that dark matter is some particle other than these 61. So we know there's at least 62 fundamental particles.
It sounds like we need to rethink this whole physics thing a little bit.
Yeah. Trying to understand what goes beyond the standard model is the thing that we're trying to figure out when we build these huge particle accelerators like the Large Hadron Collider. And we're hoping that it will give us some hint of what's out there. Now, right now, the LHC has found the Higgs, which we knew we were going to find from the standard model, but it hasn't found anything else new. And the problem is the standard model is really successful. And so we need another hint of where we've gone wrong. And so getting the Higgs, which we knew we were supposed to find, and nothing else, is what physicists, what we've been calling the nightmare scenario. that we find the Higgs, it confirms that part of the Standard Model is right, and then we don't find anything else beyond the Standard Model. This is what we're staring down right now. It's looking like the nightmare scenario is real, and unless we find something new in the new data that they're collecting at the LHC, it could be a long time before we figure out why there are 61 fundamental particles.